Good afternoon, students. Let us start the class now. In the last class, we had worked out some exercises. We will continue the same in this class as well, so that you will have a better understanding of all these concepts of information theory and about the meaning of entropy. So, look at this particular exercise. A code is composed of dots and dashes, and the dash is 3 times as long as a dot and has 1/3 the probability of occurrence of a dot. In fact, this particular exercise is related to telegraphy, which is now obsolete. The telegram has come as a app now in the 3G mobile phones. Otherwise, when Morse developed this particular method, through the electric wire, through the DC power supply, they used to transmit messages. Just a minute. Lunch bag ಅಲ್ಲಿ ಸೀಟ್ ಬಾಕ್ಸ್ ಒಳಗೆ ಒಂದು ಬಾಕ್ಸ್ ಅವನು ಹೇಳಿ ಏನಕ್ಕೆ ಅಂತ. Okay, let me resume. When Morse invented this telegraphy, they used to connect a DC power supply to the wire, telegraph wire, and there used to be telegraph operators who used to learn about this particular telegram codes, which means for A there used to be a sequence of dots and dashes. Dot means simply pressing the metal bar once. Dash means pressing that metal bar for a longer duration. So they had that symbolic representation of each alphabet in English language, and they used to press this metal bar off on for shorter duration and for longer duration, and at the other end the person used to listen to this particular electric switching of the dots and dashes, and they used to memorize these codes and they used to write the message. So that was called as a telegraph message. Tele means distance, graph means writing. So through distance they used to write the message and then he used to send it through a normal postman with the speedy delivery. So it had become very popular in those days, in the last century. And even there was a method called shorthand. Now that is obsolete. Shorthand means generally the secretaries or the personal assistants, if they had to take down a notification or one circular from their boss used to keep on telling about the circular or notification, and the steno or the secretary used to take down fast. So for each word they used to have a symbolic representation, and they never used to write the complete English word that way. Whatever boss is speaking, they used to write in the symbolic representation. Then later on they used to type the actual notice or circular in the English language. That was called as shorthand. Now that has also become obsolete, because nowadays people keep typing only using computers and mobile phones, so no need of dictating anything that way. Moreover, with the artificial intelligence, now we have speech to text conversion is possible. So such old methods no more are in use. Anyway, this particular exercise is for the Morse code transmission. A code is composed of dots and dashes, and the dash is 3 times as long as a dot and has 1/3 the probability of occurrence of a dot. Calculate the average rate of information if a dot lasts for 10 milliseconds and the gap between symbols is 10 milliseconds. So look at this, the dot is lasting for 10 milliseconds and dash is 3 times as long as a dot, means dash is lasting for 30 milliseconds. And the dash has the 1/3 the probability of occurrence of a dot. Means we can simply find out the probability of dot and dash is related by means of this 1/3 the probability. So the gap between symbols means if at all we send a telegram message, generally whenever some relative or some parents they expire, at that time people used to send a telegram, because in those days even telephone connections were rare, landline connections were also rare. They used to make trunk calls, and for remote places even telephone connections were not possible, so they used to send a telegraph. That is what was called as a P and T at that time, post and telegraph. Anyhow, now telegraph is completely obsolete. So the gap between symbols means this: if at all they send a message, father expired, start immediately. Now this father expired, start immediately. Between F and A there must be a gap, because F is a combination of dot and dash. Again A is a combination of dot and dash. In between them there must be a space. That is what is meant here. The gap between symbols is 10 milliseconds. And the duration of a dot is 10 milliseconds. Duration of a dash is 30 milliseconds. So we can find out the symbol rate, probability is also given, we can find out the entropy, and we can find out the information rate. So calculate the average rate of information. That is, we have to find out capital R by knowing small rs and knowing h. So we can easily find out small rs and we can easily find out small h, and I will show you how. You can see this. Given probability of dash is probability of dot divided by 3, which means probability of dot plus probability of dot by 3 equals 1. So this is the probability of dot. Probability of dash is 1/3 of the dot. So it is probability of dot divided by 3 equals 1. We can simply solve this expression. P of dot is 1 over 4 by 3 or 3 by 4. So naturally P of dash is 1 over 4. Now you know the probability of dot and dash. Now we know that entropy is the summation of I equals 1 to 2 of Pi Lg of 1 over Pi. So we simply use that formula of entropy to find out h. So h is 3 by 4 Lg of 4 by 3 for the dot and 1 by 4 Lg of 4 for the dash. This is nothing but Pi Lg of 1 over Pi. You already know that self-information is nothing but log of 1 over P. Please recall our earlier discussions. Lg is log to the base 2. So this is self-information. Self-information multiplied by the probability itself is collectively the entropy. That also we have seen earlier. So h equals 3 by 4 Lg of 4 by 3 plus 1 by 4 Lg of 4 is nothing but 0.311 plus 0.5. We get 0.811 bits per symbol. This is entropy. Now when this is entropy, total duration we know dot lasts for 10 millisecond, gap between this dot and dash is 10 millisecond, and dash lasts for 3 times, that is 30 milliseconds. So between a dot and a dash there must be a gap. Again between one symbol and next symbol also there is a gap. Anyhow, that we are not considering in this exercise. So now 10 milli plus 10 milli plus 30 milli, totally 50 milliseconds for a given symbol or a given character, we should say. So now RS is 2 symbols per 50 milliseconds. So the total duration is 50 milliseconds, where we are emitting dot and dash only. So RS is 2 symbols per 50 milliseconds, assuming that between the characters there are no gaps. It is a continuous stream of dots and dashes and dots and dashes. There used to be one more equipment called as a teleprinter. Now that is also obsolete nowadays. As the telegraph operator was slow in finding out The telegraph operator was slow in decoding all the dots and dashes, even at the transmitting side or even at the receiving side. They used to work out manually. Now gradually there was an equipment which was designed that was called teleprinter. This teleprinter used to pick up these Morse codes, and the teleprinter used to print as per the sequences of dots and dashes by detecting those dots and dashes. Now that machine is also obsolete because telegraph system itself is obsolete now. So this symbol rate is 2 symbols per 50 milliseconds is 40 symbols per second. Now we can find out the total information rate R is Rs into H, that is 40 into 0.811 equals 32.44 bits per second. This is one exercise. I hope you understood this particular exercise. All these exercises are simple as such, but it requires an understanding of the concept, so that you have to relate the exercise about how to use the formula for arriving at the results. Let me go to the next exercise, which is also a simpler exercise only. Only thing is you will have to understand it with the context of information theory. A black and white television picture consists of 525 lines of picture information, and each line consists of 525 picture elements. These picture elements are also called as pixels. In general, in the olden days, in the CRT TVs, cathode ray tube televisions, there used to be always something called raster, where the beam used to move from left to right, and it used to move 525 times on a screen, and the complete screen was divided again into 525 columns. So here a black and white television picture consists of 520 lines of picture information. Each line consists of 525 picture elements. That means 525 pixels are the columns and 525 lines on the screen. Total it is 525 into 525 pixels on the television screen. Now each element can have 256 brightness levels. Means each pixel on the TV can have 256 brightness levels. If at all any of you still have that cathode ray tube television somewhere, or if you have a CRT monitor for your computer screen, if you go very near to the screen and look at the screen, you can actually see all these small pixels. When you see from a distance, because of the persistence of vision, we see the picture as if it is the complete picture coming on the screen. Otherwise, each one is one pixel or picture element, it will have 256 brightness levels. So if the pictures are repeated at the rate of 30 per second, you already know that human eye has got a persistence of vision, which is about 16 milliseconds. That means if anything changes for a duration which is less than 16 milliseconds per second, let us say within 16 milliseconds, if anything changes, our human eye will not be able to detect that movement at all. That is when we call the motion pictures or movies, because it is the moving pictures or motion pictures, where there is a frame rate. Each slide is projected on the screen at a faster pace, so that we will not be individually distinguishing between the first frame and the second frame. So here the frame rate or the picture rate is 30 per second. In a second, 30 pictures are projected on the television screen. That means we cannot detect the change there. Now the question here is calculate the average information rate for this particular television transmission. Now 525 into 525, that is the total number of pixels. And here all these pixels, their probability is one and the same, which means they don't occur with different probabilities, because all of them are identical on the television screen. So they will all occur with the equal probabilities, but each pixel will have 256 brightness levels. So using this information, we have to find out the total entropy. And RS is already given. It is 30 frames per second. Now let us see how to find out the entropy. As all the pixels occur with equal probability, H is LG of 256, that is 8 bits. They are all occurring in equal probability because all pixels are identical in their characteristics. So LG of 256, they have got 256 brightness levels. So H is LG of 256 is 8 bits. We already know that entropy is LG of M. Maximum entropy can be LG of M. So that is the formula used here. The pixels probability cannot be specified separately because all are of equal probability. So H equals LG of M, that is 8 bits. Now the symbol rate is 525 pixels into 525 lines into 30. So that is 82,68,750 per second. That is the symbol. That means first pixel, then second pixel, then third pixel, like that it goes on. But each pixel can have 8 bits of information. Now multiply these. Capital R is 82,68,750 into 8 is 66.15 into 10 to the power of 6 of bits per second, or it is 66.15 megabits per second. That is the information rate from a television transmission. Now you can relate this with the audio transmission. I have been giving you the example repeatedly of the human voice transmission, that is 64 kbps that is 4 kilohertz into 2 into 8. Now look at this picture transmission. It is around 66 megabits per second, that to a black and white television transmission. If it is a color television transmission, instead of one pixel, there will be 3 pixels, RGB, red, green and blue, or sometimes RYB, red, yellow and blue. They will have different combinations. So actually there will be 3 colored pixels, different 3 colored pixels. But when we see the screen from a distance, we don't exactly identify those 3 pixels separately. We see a composite color which is emitted by all the 3 pixels. These 3 pixels will be emitting this light with the different brightness. And then we will be seeing a composite color as if there is no pixel there. Actually, there will be 3 pixels. So for the same 66 into 10 power 6, if it is a color television, you can multiply by 3. If I take it as approximately 60 Mbps, now if you multiply by 3, it is 180 Mbps. Okay, that way for video transmission, large data rate is required compared to audio transmission. In case of audio transmission, it can be in kilobits per second, whereas video transmission, it is megabits per second. You would have observed that in some of these online sessions, many times voice is breaking. When person is speaking, voice is breaking. There the system or systems network will give a priority to the video and it will give lesser priority to the audio. So in such a case, as video requires a larger bandwidth and as audio requires a lesser bandwidth, the system makes a compromise with the audio quality so that video will be transmitted. Sometimes both can be affected. Video and audio both can be affected if the system bandwidth is reduced, because it is a shared channel where many people will be using the same shared channel for audio as well as video transmission or communication. So in such situation, you can see voice breaking or even a picture getting distorted, because picture requires megabits per second and voice or sound requires kilobits per second. Both have to be transmitted separately. At times you can see that picture is seen earlier and sound is heard later. Such experience also you can see sometimes. That is because the system is giving more priority to video. So many times during our online classes, I purposely turn off the video and I purposefully disable your video as well, so that when video is completely disabled, only audio transmission can happen easily. Nowadays anyhow we are sitting in the lab. In the lab we are directly getting connected to the wired network. So by means of which now there are no interruptions. Otherwise with Wi-Fi we used to have enough issues. So all this is related to information theory. Just think about this. These are not simply some exercises. These exercises are meant for understanding the communication basics. So if speech is in kilobits per second and video is in megabits per second, together we have to transmit both of them, because video information is decoded separately, audio information is decoded separately, even though both are sent together in the same shared channel. For example, if I turn on my video now, along with my audio, my laptop will be transmitting the audio information also and video information also together. When that reaches your laptop or your mobile, there again video is decoded separately, audio is decoded separately, and then they are given to a digital to analog converter, and later on you are going to see my video or you are going to listen to my audio. So in the present scenario, when we gradually move from 3G to 4G or 4G to 5G, whichever G are coming in future, each generation of communication requires more bandwidth, because more and more of video, more and more of audio, more and more of data. Everything is now data. So more and more of data. From kbps we move on to mbps, from mbps we move on to gbps, from gbps we move on to tbps, like that it goes on. So that is the challenge. The challenge of the present technology is how to conserve the bandwidth, how to transmit less, and how to convey more. That is the challenge of the technology, and that is where the information theory is helping. Let us discuss the properties of entropy as a summary. The first property, the entropy function is continuous for every independent variable p in the interval 0 to 1. Just recall this picture where we had plotted p versus LG of p. Just recall this picture. Entropy will be maximum when the symbols have equal probability. Otherwise, this is a continuous function. That means entropy is not a discrete function. Entropy can continuously change with respect to the probability. That is the first property. Now the second property, the entropy function is a symmetrical function of its arguments. H of p comma 1 minus p is same as h of 1 minus p comma p. Again I will show the graph which we had plotted. You can see from the maximum entropy to the left side and to the right side, the entropy function is symmetrical. P and 1 minus p are actually having a symmetrical entropy. That is the second property. Now let me come to the third property. The entropy attains a maximum value when all the source symbols become equiprobable, that is H max equal Lg of m bits per symbol. This is already known to us. Fourth one is the entropy does not get reduced when the symbols are split into sub-symbols. This is important. For example, we had a discussion of telegram where we only consider this dot and dash as such, and each alphabet is represented by means of a sequence of dot and dash. We did not discuss about that message. Let us say father expired, start immediately. If that message goes, then between F and A there must be a gap, between A and T there must be a gap. That we did not discuss. Why I give this example only, you may wonder. Because olden days, whenever telegram used to come, people used to become afraid. Because telegram used to come only when there used to be some sudden demise of a family member. That's why I kept on giving the example of father expired, start immediately. Which means that father is no more, son has to immediately reach to the hometown or to the home village or wherever father was staying, so that the son can conduct the after death rituals. So even in the old movies, still if you watch any old movies, still this particular scene will be there where the postman will simply say telegram, and immediately the family member's facial expression will change, because telegram used to be sent only in emergencies, that too for situations of calamity. Now, let me come back. Let me not give any crazy examples. The entropy does not get reduced when the symbols are split into sub-symbols. Why I told that example? Let us say between that FATHER, F is containing dots and dashes, T is containing dots and dashes, A is containing dots and dashes. That way the word father is constructed. Now, if we take this father itself as one symbol, we split it into sub-symbols as FATHER. That is one example. One more example is F itself is a symbol, F is split into dots and dashes there. Now, a symbol is split into sub-symbols. Even with the sub-symbols, if we take up the self-information of each dot and each dash, and when we calculate the total information content of a given character, the entropy does not get reduced. This we have seen already. I of M1 and M2 is nothing but I of M1 plus I of M2. This we have seen. So, even if this M1 and M2 are split into sub-symbols, let us say M11, M12 and M21, M22, split into sub-symbols, even then the entropy does not get reduced, because the I of M1 is nothing but I of M11 plus I of M12. For example, if the character A contains dots and dashes, then the information content of A is nothing but information content of dot plus information content of dash, which is contained in that character A. So, if the symbol is split into sub-symbols, entropy will not get reduced, it will remain the same. For this particular property, the last property, we have an exercise later on. You will understand this much better later on. So, the third property is called as extremal property. The third property means the entropy attains a maximum value when all the source symbols are becoming equiprobable, or H max equals LG of m bits per symbol. This is called as extremal property, and the fourth property is called as the additivity property. Means if a symbol is split into two subsymbols, the entropy will be anyhow addition, no? I of M1 plus I of M2 equals I of M. So, that way the entropy of each sub-symbol gets added up to the main symbol. That is called additivity property. Now, the efficiency of the source is given by eta s equals h by h max. We know that h max is nothing but Lg of m, and we know that whenever any normal information source is there, the probability is not equal. The probabilities of all the symbols are equal only with the example which we told today, that is the television picture, where all pixels are identical. Whereas, if at all we take the English language for our example, there the probability of A to Z is not equal. So, efficiency of a source is given by H is the real time entropy, H max is the maximum entropy. That is the efficiency. In general, efficiency of any system is given by output divided by input. But here in case of information theory, it is not so. Because you know that the maximum entropy is nothing but Lg of m. And the normal entropy is always less than the maximum entropy. So, efficiency will be 1 only when the real time entropy is equal to the maximum entropy. Otherwise, efficiency is always less than 1. So, if that is the efficiency, then there is the redundancy which is given by R eta s equals 1 minus eta s. If at all we represent this eta between 0 and 1, now let us say the eta we get for a particular system is 0.8. Now, R eta s or redundancy is given by 1 minus 0.8 is nothing but 0.2, which means that the system contains 20% redundancy. Now, in the case of a television picture, H max and H both are one and the same, because all pixels are of equal probability. Their eta is 1, that means redundancy is 0. Then we should say that this particular example of the television picture is the best information source where there is no redundancy at all. More the redundancy, lesser will be the efficiency. Why? More the redundancy, unnecessarily we are wasting our resources for the redundant information. As you already know, the one which is more probable is less informative. The one which is less probable is more informative. So we will have to convert this probable thing into informative thing. So if the redundancy is more, actually information will be less. That is how redundancy is nothing but 1 minus eta or 1 minus efficiency. Based on this, let us have one more exercise now. Can you do it on your own? I will give you 2 minutes time. A zero memory source means the source is having a statistically independent alphabets. S equals S1, S2, S3 with the probability of half, 1/4, 1/4. Together you will have the total probability unity. Find the source efficiency and the source redundancy. It is an easy problem. Do it quickly within 2 minutes. Tell me the answer and put the answer in the chat box. Okay, Chandramohan has given the answer H is 1.5. Vanilla has given the answer 94.6%. Kuldeep has given the answer 94.6%. Okay, let us see the answer. H max has to be 1 over 3. When all 3 are equiprobable, this S1, S2, S3 will be 1 over 3. H you can find out using this information itself. Summation of Pi into Lg of 1 over Pi. So that way, H of S is half Lg of 2 plus 1/4 Lg of 4 plus 1/4 Lg of 4. You will get 1.5 bits per symbol. That is H of S. That is correct. Next, H of S max is Lg of 3 because there are 3 symbols. Lg of M is nothing but 3. They must be equiprobable 1 over 3, 1 over 3, 1 over 3. So this is 1.585 bits per symbol. So now eta is 1.5 divided by 1.585 is 94.64%. That is correct. So the redundancy is 1 minus this 0.9464 is 0.0536, means it is having a 5.36% redundancy. That means the information source is having around 5% redundant and around 95% efficient. Okay, now this is a slightly different problem. Consider a discrete memoryless source with S equals S1, S2, S3, 3 symbols with the source statistics as 0.7, 0.15, 0.1. This is the probability. Verify that the entropy of the second order extension of the source is H of S square equals 2 into H of S. This I will not ask you to solve. I will show you the solution here itself, because here we are splitting each symbol into the sub symbols. That is called as second order extension. How do we do it? Let me show you. That second order extension is called as S square. Otherwise, don't think that we are squaring the information source itself. It is not that way. This is simply a notation. Through this notation, we say this is a second order extension. Now, the second order extension is equivalent to 2 into h of s. Now don't relate this with the subsymbol concept directly, because it is an extension, it is not actually a splitting of the symbols as such. I will show you the solution. So let us find out h of s now. H of s is 0.7 Lg of 1 over 0.7 plus 2 into 0.15 Lg of 1 over 0.5 as the information is given, and h of s is 1.1814 bits per symbol. The probability of the second order extension, they are written this way: P of S1 S1, P of S1 S2, P of S1 S3, that way it goes on. This is an extension, this is not a breaking up. Please understand that. So P of S1 S1 equals 0.7 into 0.7 equals 0.49. Okay, there was a slight disruption. I will continue now. The probabilities of the second order extension, again I am reiterating, it is not the breaking up of the symbols, it is simply for the sake of illustration. It's an extension, means symbols can be combined together to have an extension. So P of S1 and S1 is 0.7 into 0.7 is 0.49. Similarly, P of S1 S2, S1 S3, S2 S1, S2 S2, S2 S3, lastly S3 S1, S3 S2, S3 S3. This is the combination of the individual symbol with the other symbols. Now this is going to be the probability of all of them, because you know from your learning of the probability and statistics that when there are two occurrences, the probability gets multiplied there. So now h of s square, this is the second order extension. H of s square is calculated for all these probabilities in this manner. There are repetitive values, that is why I have put 4 into and 4 into here. So h of s square is finally 2.3628 bits per symbol. Now we have found out h of s also. H of s is 1.1814 bits per symbol, whereas we are reusing same symbols again and again. That is second order extension. So then h of s square is 2 into h of s. This is proved by means of one particular exercise. So in general, it can be derived that h of s power n is n into h of s. Means when an information source's symbols are combined together and when the extension is performed, the information content is actually increased by the number of extensions. Which means if we combine two symbols together and we use that two symbols extension to transmit information, the information also becomes double. Same way, it depends on how many number of symbols we use together, that many number of times the information gets increased. Now this is obvious. Why? Because we are going to use, see here we are going to use two symbols for each transmission together, means naturally the information is going to increase. So again I repeat, this is not breaking up of the symbols, this is combining of the symbols. Don't get confused. Now let me tell you about the another example. A discrete source emits M1, M2, M3, M4, 4 symbols with probabilities given like this. Show that the entropy of the source increases when M4 is partitioned into 3 subsymbols with the probabilities 1 over 24, 1 over 60, 1 over 120. Here M4 is partitioned into 3 subsymbols. This itself 1 by 50 is partitioned into 3 subsymbols where each symbol is containing 1 over 24, 1 over 60, 1 over 120. Now, we had shown earlier that when subsymbols are split, entropy does not get reduced. That we have seen. But at that time, we did not tell you that entropy will get increased. Now we have seen in the second order extension that entropy is getting increased. Now here also, when this last symbol M4 is split into 3 subsymbols with the different probabilities, even though the total is 1 over 15, the total information gets increased. Reason is that M4 is represented by means of 3 subsymbols. So, if we split a symbol into subsymbols, naturally the information content is going to be more, so entropy is going to increase. There we have told as one of the properties as entropy will not get reduced, but entropy will not remain equal to the previous entropy also. Entropy will get increased. That we will see in this exercise. Now let us find out h of s. H of s is directly, I am going to show you the answer, 1.7467 bits per symbol for the given probabilities. Now let us calculate this M4 when it is getting partitioned. Its respective information content is given by I of M4 is again, we will find out the entropy of this M4 itself. That we get as 0.3472. Now we will use this with this h of s, just to call it as h of s dash. So here you have 0.5132, 0.5086, 0.4644. The last one is going to change now. So here it is 0.5132, 0.5086, 0.4644. When you split it into subsymbols, here it is 0.3472. So the total information, which we have called it as h of s dash. Why we called it as h of s dash? Because we have split it into subsymbols now. It is not an extension again. Don't get confused. It is not h of s square or h of s cube. It is not an extension where all the symbols are not extended. One particular symbol is split. So h of s dash is 1.8334 bits per symbol, which you compare with this 1.7467, information content is increased. So the conclusion is h of s dash is greater than h of s. Any type of splitting of the symbols is going to increase the information rate. That is the conclusion. This is where I end all the basics of information theory. From the next class onwards, we will go into a little detailed topic called Markov source, or it is also called as Markov source. So now in the Google class, I am going to post the quiz links, and US number 1 to 25 go for set A, US number 26 to 50 go for set B, US number 51 onwards till the end go for set C. That link I have already posted in the Google class. Go back to Google class and check it now. That quiz attempt itself is considered as attendance for today's class. So we will see you in the next class. Bye bye.